Hey, welcome back to another video of Chem with Com. Today we're going to be doing stoichiometry. This is a four-part series. This is the first one, and this is just called Stoichiometry Basics. Now, this is one of the most abstract and difficult concepts for chemistry students to kind of absorb and really understand. But at the same time, it's one of the most basic math things that we'll do in chemistry. So it kind of is counterintuitive, right? But give yourself some time to learn this, some space, some grace, right? Because you're gonna have difficulty having it click. But once it clicks, you're all good. So just maybe watch this video a few times, take other notes, look at other videos. But I'm going to try and break this down into a really understandable format. All right. All right, let's get started here. All right. Stoichiometry basics. Again, four-part video series. Maybe do this one. I recommend not moving on until you really understand this. All right. Okay. So this is sort of a continuation from topic 6. So go back and review that. It's measurements, prefixes, and dimensional analysis. It's the very last part. This is a continuation, sort of dimensional analysis. It's very related. Um, and it's again, look at that part 4. And this is what we left off on. This is a little conversion table I made. We're going to build on this and make a more complex one, but for now, this is what we left off on topic 6, part 4 of 4. So review that video if you need some help with that. Okay, stoichiometry expands on this table or this conversion kind of tutorial I set up using the mole ratio. Okay, we're adding this new number to our conversion table. And it's basically use the mole ratio of the chemical equation. So we're going to look at a chemical equation. I gave you an example here. And we're just looking at the ratio of the different materials, the different reactants and different products within that chemical equation, right? So for example, the ratio for H2 diatomic hydrogen to ammonia, NH3, is a 3 hydrogen, because that's what we have here in the chemical equation, and 2 ammonia, right? 2 NH3. So that's all we're going to do. We're going to use those small ratios to be able to go back and forth between different products and reactants within a chemical equation. All right. So let's go back to food because this is what I like talking about. A recipe lets you know how much you can make or how much you need of things and how much you can make of something, right? That's what a recipe does. Um, for example, we have a recipe to build a sandwich. This sandwich is made by using 2 pieces of bread and 1 piece of cheese, reassembling those parts into um, another thing, which is the sandwich, right? And that's the ratios we're talking about. So we have 2 bread to 1 cheese, right? We know that. We also know there is 1 cheese for every 1 sandwich. We also know there is 2 bread for every 1 sandwich, right? These are the ratios of ingredients to other ingredients, of ingredients to products, and of other ingredients to products, right? You can go back and forth between all of these. What's really important is recognizing these numbers in red as what's called the stoichiometric coefficients. I know it's a lot of vocabulary, but these are the coefficients. We've talked about them before, especially when balancing. And they're going to tell you again how much we have to use to make a certain amount, right? So let's take a do question. If we have 10 bread, right? If we have 10 pieces of bread, how many pieces of cheese do we need? We want to make a bunch of sandwiches, right? So if we have 10 bread and we want to make sandwiches, what's the ratio of bread to cheese? Well, we know that. The ratio is 2 bread to 1 cheese. Because bread is here, I want to put the bread on the bottom here. 1 cheese, right? So we're comparing bread to cheese because we know it's asking how much cheese do we need if we know we have 10 bread. So we're going from bread to cheese. The bread is what we know. So 10 bread, look what cancels out. Bread cancels out and you get 5 cheese, right? So we'll say 5 cheese. If we have 10 bread, we need 5 pieces of cheese to make all those sandwiches, right? Let's do another one. Things getting a little delayed here. All right, let's do this one. If we have 20 sandwiches, how many pieces of bread do we have? So here we're going from, let me erase this part. For this specific question, they're asking, hey, if we have 20 sandwiches, how many pieces of bread did we need to make those 20 sandwiches? Well, we're going to use the mole ratio of bread to sandwich. So this one, because those are the two items that we're interested in. We know how many sandwiches we have. We're looking for how much bread we needed to make those sandwiches. All right, so we're going to put the 1 sandwich on the bottom and the 2 bread, right? Well, look what cancels out. Sandwiches cancel out, and it gives us our answer. We have 40 pieces of bread, right? So we'll say 40 bread. All right, let's do the last one. If we have, let me just erase this again. Sorry, it's so slow today. Oops. Okay, let's do this last one. If we have 3 cheese, how many sandwiches can we make if we had unlimited bread? Right? Okay, so we're going to use now cheese to sandwiches. Because we have 3 pieces of cheese, unlimited bread. We don't know how much bread we're going to need for this, but we have unlimited. We're not going to run out. We're going to use that ratio. Since we have cheese on top here, we're going to put cheese on the bottom, right? And you could probably have done this without doing the math, but it's very, very important to do these easy examples so that when you do the difficult problems, you have somewhere to come back to kind of ground yourself, right? Because it gets pretty overwhelming here for this chapter. Like I said, it's not you guys learning, it's just the way chemistry is. It's a very, very difficult, vague topic, but with simple math, right? All we're doing is these small fractions. All right. So we're going to cancel out the cheese, and then we can make 3 sandwiches, right? And this is the slide you want to come back to, the video you want to come back to when you get stuck with these more difficult concepts, right? And we're finished there, right? So we calculated all that using what's called the ratio, right, of ingredients to products, or even within the 2 ingredients, or it could be 2 products. It doesn't matter. It lets you relate everything in that recipe, right? So a recipe lets you know how much you need of things and how much you can make of something, right? That's basically what a recipe is. Now, if we go forward just a little more chemically, right? A balanced equation lets you know how much you need of things and how much you can make of something. It's exactly the same thing. Now, what's more difficult is the terminology, and you're saying silver instead of bread, and you're saying sulfur instead of cheese, and you're saying silver sulfide instead of sandwich. You're just changing the words, but everything is exactly the same. Remember, we had two pieces of bread, one piece of cheese, and we had one sandwich. Atoms of silver, one atom of sulfur, and you can make one molecule of silver sulfide, right? And these are the ratios, right? We have two silver to one sulfur. We have one sulfur to one silver sulfide. We have two silver to one silver sulfide, right? And again, this is just like the sandwich example. This is a specific ratio called a mole ratio. We've talked about it before, but this is where we're really going to hammer it home. This is called the mole ratio, and this is the center of stoichiometry, right? Let's answer the exact same questions we answered earlier with just these atoms and molecules now. All right. If we had 10 silver, how many sulfur do we need? So we're trying to figure out, we're going to go from silver to we're trying to figure out sulfur. And we're going to use this, what's called the mole ratio, because it involves the silver and the sulfur. And I'm going to change this to chemical formulas and element symbols just so we could get a little more technical here, right? So we have 10 silver. How many sulfur do we need? Well, since silver's here on top, we want to have two silver on the bottom. And I'm going to change the words a little bit just so we can get used to this. And I'll explain that in a few slides of why we're doing this. But for now, let's just say 2 moles of silver. Okay. Um, the mole ratio is 2 silver to 1 sulfur. Right? Okay. So let's figure this out. Right? Look what cancels out. The silver cancel out and moles cancel out. Right? So then we're left with 5 sulfur. I'm just going to put 5 here. Oops. Okay. Let's look up here. And look, 5 cheese, right? Exactly the same calculation. Let's do another one. 20 silver sulfides. Let me clean this up a little bit. Hopefully that worked. All right. All right, so let's try 20 silver sulfides. So just like sandwiches, right? We had 20 sandwiches, but here's 20 silver sulfides. We're trying to see how many silvers we have in there. So we're going to use the silver to silver sulfide ratio. And again, whatever we're trying to cancel out, we're going to put on the bottom of the fraction. So 1 Ag 2S. And you could put mole or not, but I'm going to show you, we're talking about the mole ratio, right? And because, yeah, I'll show you, like I said. Let me just continue this. 1 mole silver sulfide to 2 mole silver. Well, look what cancels out. Silver sulfide cancels out, and the moles cancel out, and we get, oh, sorry, 40 silver atoms. Sorry, it keeps doing that. And I'm going to write here 40. And again, that was our last answer as well. And let's do this third one here. Let's erase this. Don't know why it keeps doing that. Sorry. Okay. So let's do this last one. We have three sulfur, where they're asking how many silver sulfides you can make if you have unlimited silver. So we're using that equation now. So we have, again, we're starting with three sulfur. We're multiplying by the mole ratio. We're going to put the sulfur on the bottom. So it's 1 mole sulfur. It's probably irritating for you guys too. Sorry. I think maybe it's hitting my phone or something. All right. And, oh, sorry, I wrote that out. It's just to be a symbol. I forgot. Sulfur cancels out. Moles cancel out. We're left with now three silver sulfides. All right. Just like we had three sandwiches in the last one, right? Three sandwiches. So it works exactly the same for these chemicals, right? And the problem is when you click over from sandwich to silver sulfide, you lose a lot of that mobility and that ability to be able to use mole ratios. All right, let's do this again. The mole ratio works for food. Let's check this out. All right, here we're making egg noodles, right? So we have a pack of eggs, 3 packs of flour, and that'll give us 2 boxes of noodles, right? And again, it's a 1 to 3 ratio between pack of eggs to flour, 3 packs of flour. It is a 1 to 2 ratio where we have 1 pack of eggs to 2 boxes of noodles, right? And we also have the ratio of this here, 3 packs of flour to 2 boxes of noodles. All right. So yeah, let's look at the ratios now. And we're just centering on this one because we don't have enough space to talk about all of them, but I want to recreate this with something more complicated, right? We have 3 packs of flour to 2 boxes of noodles. Well, let's say we needed a bunch of noodles, right? We can increase that to 3 dozen packs of flour, and that'll allow us to make 2 dozen boxes of noodle, right? The only thing that changed was this dozen, right? And you need, of course, you need eggs with this, but this is just specifically talking about the ratio of flour to noodles. And you could do eggs to noodles and you could do eggs to flour, right? Again, we can be very mobile with this. We just have to make sure we're very confident in what we're doing, and that's what we're doing right now, right? We can't just kind of putz around here, but we really need to put the numbers and the units and everything in the right spot. All right, let's say, boom, we served it at a party. Now Costco was like, maybe the CEO of Costco was there, and he's like, you know what? I love these noodles. Scale it up. We're gonna sell them in Costco's across the country, right? So we increased that to now 300 packs of flour, and that'll allow us to make 200 boxes of noodles, but the ratio is still the same. It's still a 3 to 2 ratio, right? That's the ratio. It doesn't matter what we put in front of that. And we can say 3 moles of packs of flour and 2 moles of boxes of noodles, right? That would be feeding the entire world uh, for the next billion years, right? There's so many in a mole. And this is how much a mole is, right? So that's all you're saying is when you're talking about the mole ratio, you're just talking about a huge amount, but that's called the mole ratio, right? And I just wanted to show you the value of a mole, which is 6.022 times 10 to the 23rd, anything. But again, this mole ratio works for food. And let's try it with now chemical equations. We're going to do exactly the same thing we did. And let's do that here. So we have 1 pack of eggs, 3 packs of flour, makes 2 boxes of noodles. All right. Let's see. Video panel gone. All right. So this is the ratio, right? And we have 1 diatomic nitrogen to 3 diatomic hydrogen. makes two ammonia or NH3, right? And if you count the atoms, it's all there. We're starting off with two nitrogens, we're ending with two nitrogens. We're starting off with six hydrogens, we're ending with six hydrogens. But we're looking again at the products and reactants, and we're looking at the ratio of specifically those molecules, right? So here we have 1 N2 to 3 H2. That's the mole ratio of reactants to each other. Here we have one diatomic nitrogen to two ammonia. And here we have three H2 to two NH3, right? That's the ratio. Okay. And we're going to expand on this last one just because we don't have room to do all of them, but it works the same for all of them. So you have 3H2 to 2 NH3. You also can do 3 dozen H2 to 2 dozen NH3. You can do 300 H2 to 200 NH3. 3 moles of H2 to 2 moles of NH3. Again, this is all a 3 to 2 ratio. And this is what we're going to be using is the mole ratio for all of them. And again, this is just the number representation of a mole, just to keep you kind of focused on it, just a number of things, right? Okay, the mole ratio works for molecules as well, right? This sandwich, in a sandwich, we know there are two pieces of bread and one piece of cheese. So mole ratio, two bread, one cheese. One cheese, one sandwich. Two bread, one sandwich. Well, this works within a molecule as well. Let's look at water. Water has two hydrogens and one oxygen. So the ratio is two hydrogen to one oxygen. One oxygen to, for each one water, there's one oxygen there, right? This is for each one water, there are two hydrogens. Let's circle those. This is the oxygen, right? And this is the oxygen. This is the two hydrogens. This is the two hydrogens, right? We're looking at ratios, and this is the mole ratio of a molecule, right? So it works for both. So the mole ratio is used for calculations involving various products and reactants, as well as atoms within molecules. If you're looking for atoms within molecules, we've done this before already, back in chapter, I believe it was topic 6, right? The dimensional analysis. But we've already used this. We didn't formally, address it as long as this because it was just kind of a simple concept, but this is where it gets a little more difficult. So number 3 here is where you're going to go from atoms within molecules or molecules to atoms. You're going to use the mole ratio of the atoms within that specific molecule. Like we did water. Here, if you look at BAF2, you could see that there are two fluorines, right? Two atoms of fluorine for every one molecule of BAF2, which is barium fluoride. All right, we've done that before, just lightly. But now what we're going to do is we're going to introduce this other one here, where we're going to use the mole ratio, again, of the chemical to now be able to move back and forth between reactants and products, or between two reactants, or between two products, right? Just to figure out how much we need of stuff, how much we can make, and things like that. That's our. All right, so this is one important part when we're using this little table of conversions, right? We're going to use this dotted line here as our separator between two different formulas, right? So let's say I wanted to look at fluorine. Oops, let me fix that. Let's say I want to look at atoms of fluorine within one molecule of BAF2. And it says you're going to assign one thing up top and the second thing on the bottom, right? So here I'm just going to write fluorine. Here I'm going to write the whole BAF2. And since we're going from atoms to within molecules, right? F is within barium fluoride, right? You can see it's in there. We're going to use the mole ratio of atoms within the molecule. So we're going to use this arrow here, and we're going to go back and forth, or we can go back and forth, and that'll allow us to convert atoms to molecules or molecules back to atoms, right? All right, let's look at the other one now. So let's say now we're trying to go back and forth between, let's say we're trying to figure out, we have a certain amount of H2 and we're trying to see how much NH3 we can make, right? So let's say H2 here, since NH3 is a different formula, you write it on the other side of this dashed line. Atom or molecule must have the exact same formula and cannot cross this dashed line without using number 3 or number 4, right? So we cannot cross that dotted line without using number 3 or number 4. And these are two different formulas, right? So since they're two different formulas, you set them on opposite sides of this conversion table. Okay, and we get through number 4 by using the mole ratio of the chemical equation. 3H2, which is here, to 2NH3, which is here, right? So again, we'll do some practice at this later, but this is just showing you how to use this table and kind of giving you further instructions, right? All right, let's continue. So here's a problem that's going to come up, and it gets more complicated, right? So they're saying the title is moles of reactant required in a reaction. They're saying how many moles of I2 are required to react with 0.429 moles of aluminum. So they're saying, hey, in this chemical equation, we know how much aluminum we have. We're trying to figure out how much diatomic iodine, or I2, we need to be able to react those 0.429 moles. Let's look at the ratio here, right? 2 aluminum, 3 iodine, right? 2 to 3. We could double that, right? But we have to double both, and it's still a 2 to 3 ratio. You can multiply both by 10. It's still a 2 to 3 ratio. You could even go in decimals, right? You could have 1 here, but since it's a 2 to 3 ratio, you have to have 1.5 iodines, but it's still a 2 to 3 ratio. All right, you can do decimals here, smaller decimals, 0.5. Well, it still has to be a 2 to 3 ratio, so it makes it 0.75 of iodine, right? And here is where we're actually doing the problem, right? We're going to do 0.429 aluminum to 0.6435 iodine, and that's still a 2 to 3 ratio, right? So how the problem works is just like before, we write what we're trying to do, or trying to convert, or trying to analyze, right? They're saying, hey, we have 0.429 moles of aluminum. Apply that by the mole ratio. And we're going to put aluminum on the bottom, right? And moles of aluminum cancel out with moles of aluminum. So we're left with now moles of iodine. So 0.429, let's break out a calculator here. Hopefully you can still see this. So 0.429 times 3 divided by 2. 0.6435, and that's what we got. 0.6435 moles of iodine, right? And so what we did here is we went from aluminum to iodine, I2, right? This is our start where we started, right? Because they're telling us, hey, it's 4.429 moles of aluminum. We're going to go to now moles of iodine. And we're going to use the mole ratio of the chemical equation, which was 2 aluminum to 3 iodine. And this is our end. And we're done, right? It's complicated, right? If you're getting confused here, go back a few slides, watch it over again. Stop it, make notes. Again, this is a very, very abstract concept. As you can see, the math isn't crazy difficult. It's 3 times 3 divided by 2, right? But conceptually, this is a very difficult thing to have click, especially right away. It took me a long time to get that to click for myself. All right, let's do some practice problems. How many moles of H2 do we need to fully react 2 moles of N2? So let's write this down. We have 2 moles of N2. We're trying to get to moles of H2. So we're going from H2 to N2. Let's write down the ratios. And I'm going to write them in 2 different fraction forms. I'm going to say 1, or let's do the equation first. 1 and 2 equals 3 H2, right? This is what that means here. This 1, and there's no number, right? It's going to be a 1. I'm not sure if I can write up there because it's too close to the top. There you go, 1. So the 2 fractions it's going to be are, we can either have 1 and 2, or I'm going to fix this here. I'm going to write down moles because we want to be able to really focus on mole ratios. I want to make sure there's that word in everything. 1 mole N2 equals 3 moles of H2. Let's do 2 fractions. We're going to say 1 mole N2 over 3 moles of H2. Here we're going to say 3 moles of H2 over 1 mole of N2. All right, let's try it. So we have 2 moles of N2. We want to figure out H2, so we need N2 on the bottom, which is going to be this one. So we're going to use that one. It's going to be 3 moles H2 to 1 mole of N2. All right. So we're going to look what cancels out. Moles of N2 cancel out. It's just 2 times 3 divided by 1 is going to be 6 moles of H2. All right. That was number 1. Let's do number 2 now. We got to figure out what's going on with that here. I'm going to draw a line to separate us. All right. Number 2. And it says, how many moles of H2 do you need to synthesize 12 moles of NH3? That was a bomb here. NH3. Maybe I'm pressing the button. Let's see here. And we're trying to get to moles of H2. All right. I'm going to do this without making those fractions. I'm just going to come up here and underline what I'm trying to use. So now we have 12 moles NH3. I know just because of units, I'm going to need on the bottom moles of NH3. And here we have a 2, so that has to be a 2. Okay, since I'm trying to get to moles of H2, I'm going to need H2 up top. So I'm going to say here moles of H2. And here I have a 3, right? It says 3, so we have to use the 3. All right. So look what cancels out. Moles of NH3. 12 times 3 is 36 divided by 2. I believe this is a 18. Let's see. H2, what are we doing? NH3. 12 times 3, 36 divided by 2 should be 18. And that's going to be moles of H2. That's how many moles of H2 we need to synthesize 12 moles of NH3. It had nothing to do with the other ingredient. We're just checking that one reactant or the one ingredient, right? When we do problems like this, we're just assuming we have unlimited of the other one. And we'll do more examples of that. Okay, 3. If we have 1.5 moles of N2, how many moles of NH3 can we make if we had unlimited H2? And that's very, very similar to problem 2. We just put that last kind of phrase, can we make if we had unlimited H2? But it's the same thing. We're starting off with 1.5 moles of N2. We're trying to figure out how many moles of NH3 we can make, right? We're just going from a different, we're saying, uh, yeah, sorry, I think I misspoke over here. So number 2, right? Yeah, we're trying to synthesize 12 moles of NH3, but we're asking how many moles of H2 we needed. So this is almost the same thing, but now we're starting from an ingredient going to the product, right? Which is a little different, but it's the same exact concept. We're going to start with 1.5 moles of N2. And since we know, I'm going to erase a couple things here just so we could show that. And on the bottom, just unit-wise, we know we're going to have moles of N2. If you look at the ratio, since there's no number, that's going to be a 1. We're trying to go to NH3, and here we are, 2 moles of NH3. All right, so let me let that to kick in. Sorry, it takes a little bit. Look what cancels out. Moles of moles of N2 cancel out, and we can make 3 moles of NH3. Again, mole ratios, right? All you're doing is looking at coefficients. You're kind of, if you think back to our dimensional analysis and conversions, we're converting from one reactant or product to another reactant or product, right? And we're using our equation, our conversion rate. We're using our fractions, right? We're doing exactly the same thing. So if you want to think about this as converting one reactant to another reactant, or one reactant to a product, or product to reactant, you could do it that way. And it's exactly the same procedure as converting, right? And there's no difference. The thing is, we had to make our conversion rates for that, right? So let's try another one. All right. How many moles of calcium hydroxide are required to react with 1.36 moles of phosphoric acid, right? To produce phosphoric acid. Yep. And then to produce this calcium phosphate, right? So we're looking here. I'm going to write the question down. We're starting with 1.36 moles of phosphoric acid. And they're saying, hey, how many moles of calcium hydroxide do you need to make this stuff, this calcium phosphate, right? And this is CaOH close parentheses 2, right? We're trying to figure out here. All we're going to do is use the mole ratio, right? So we have 3 here and we have 2 here. So we're going to start 1.36 moles H3PO4. I guess maybe the wire's getting touched. I'll figure this out. All right, so now we're going to multiply by the mole ratio. And since we know this is on the bottom, sorry, this is in the original value we're trying to kind of use to figure out the other value. There is a 2 in front of that phosphoric acid. So it's a 2 moles NH3. And here is 3 moles calcium hydroxide. All right, look what cancels out. This cancels out. Moles of phosphoric acid cancel out. Let's do units first. Now we know we're going to be left with moles of calcium hydroxide. If you do your units, it's an easy way to check your work without having to actually check your work, right? All right, let's do the math. So it's 1.36 times 3 divided by 2. Let's use a different calculator. I think it's 1.36 times 3 divided by 2. So I got 2.04. Let's talk about this real quick, right? If I have 1.36 moles of phosphoric acid, I need 2.04 moles of calcium hydroxide, right? And let's look at this. It's going to be let's look at this. Let's do it kind of just visually to see if we could figure out if this is actually true. And the ratio is 2H3PO4. All right, let's do this. This is the ratio. Let's do all right, so we're starting with let's do this. Let's do so it's a 2 to 3 ratio. That's the same as 4 to 6. That's the same as a 1 to 1.5, right? Because it's 2/3. And then our answer is 1.36 to 2.04. And these are all a 3 to 2 ratio. That's all we're really doing is we're just figuring out the ratios between the reactants here. But you can go products to reactants, reactants to products. All right, that's it. Again, don't move on from this video until you understand at least 95% of this, because the other stuff, there's not much explanation. We're just going to do a bunch of practice problems. All right, so try that. And yeah, let me know if you need anything, but I'll catch you next time. Thank you very much.